Day 17 of 60, and today Rust is going to reject your matrix code on purpose. Try transposing a vec 32 in place, and you write let row underscore equals mut grid I, let row underscore j equals mut grid j, and boom. Cannot borrow grid as mutable more than once. Two mutable row borrows into the same outer vec. Most tutorials call this a fight with the borrow checker. It isn't. It's Rust telling you your data model is wrong. And by the end of these 5 minutes, you'll model matrices the way both the compiler and your CPU actually want. Here's the redesign. Instead of a vector of vectors, we store one flat buffer. Struct matrix t data, vect, rows, usize, calls, usize. A nested vec t is one allocation per row, scattered across the heap, pointer chasing, and cache misses for free. The flat vec is a single contiguous allocation. To find element row R, column C, you compute the index yourself, R asterisk self dot calls plus C. That's row major order, the same layout C uses. One allocation, explicit index math, and the borrow checker now reasons about a single vec instead of a tree of them. We give it two accessors, fn get, self, R, usize, C, usize, t self.data, R asterisk self.calls plus C, and a get underscore mut that takes mut self and returns mut t. Notice the borrow story. Get borrows the whole matrix shared, get underscore mut borrows it exclusively. That's the contract. You can't hold two mut t into data at the same time through these methods. And that's exactly the rule that bit us with nested vecs. The difference is that now the fix is clean instead of a lifetime puzzle. So how do we transpose in place? For a square matrix, we swap element R, C with C, R for every cell above the diagonal. Naively, you'd write let A equals self to get underscore mut R, C. Let B equals self to get underscore mut C, R. Two mutable borrows, instant rejection. The trick is vec, swap. It's the one operation that legally touches two mutable positions in the same vec, because it takes two indices, not two references. Let I equals R asterisk self dot calls plus C. Let J equals C asterisk self dot calls plus R. Self.data.swap. IJ. You only ever name indices, never overlapping mut-s. 3 lines, 0 clones, fully safe. The borrow checker is satisfied because swap proves the accesses don't alias. Now matrix multiplication, where the borrow split really shines. You're writing into an output matrix while reading two inputs. The signature, fn matmul, A, matrix 64, B, matrix 64, out, mut matrix 64. Both inputs are shared. The output is exclusive mut. Because out is a separate allocation from A and B, the compiler verifies non-overlapping access with no clone anywhere. Inside the triple loop, you accumulate some plus equals a.get, I, k, asterisk b.get, k, j, and then asterisk out.get underscore mut, I, j equals sum. Reads from the inputs, one exclusive write to the output. The ownership lines up with the math, shared things you read, owned things you write. Step back to the interview lens. In a garbage-collected language, every algorithm variant looks the same. In Rust, the ownership model changes which variant you reach for. In-place transpose needs mut self and swap. Multiplication into a fresh buffer wants inputs and a mut output. The moment an algorithm needs two mutable windows into one structure, Rust pushes you toward index-based swaps or split under mut. That constraint isn't friction. It's a design hint about whether your data should be owned, borrowed, or restructured entirely. And the flat model composes upward beautifully. A sparse matrix in CSR format is just 3 owned vecs, values, call underscore indices, and row underscore pointers, living in one struct. When you iterate a row with row underscore pointers, R, row underscore pointers are +1. Each slice is a non-overlapping shared borrow, so they compile cleanly and even parallelize. Swap a plain iterator for rayons par underscore iter over rows, and you get safe parallel multiplication with 0 unsafe. Owned vex crossing struct boundaries, no lifetime annotations needed. So the lesson, the flat vect matrix isn't a Rust workaround. It's the correct memory model. One allocation, row major index math, and a borrow story. The compiler can actually verify. Use swap for in-place moves, split shared inputs from a mutable output for multiplication, and let ownership tell you which algorithm variant fits. Day 17 done. Your key takeaway. Model the data right and the borrow checker stops being an obstacle and starts being a proof. Subscribe for day 18.